For part one of this lecture, we're going to talk about proportions as probabilities. So I want to start with this idea of measures of association. We often want to see how two variables are related. And so for this week, we're going to think about two binary categorical variables. This kind of association that we're really building up to, this idea of relative risk, is based on probabilities. So in order to understand relative risk, a basic measure of association, we have two categorical variables that are binary. We really need to understand the basics of probabilities. Probabilities are really a way of expressing findings in terms of more or less likely. So you might say, well, people are more likely to smoke cigarettes if they are less educated, for example. We see this kind of language used a lot in research. This is built on the basics of probability. So let's begin with this example of health insurance. Suppose you're an epidemiologist and you want to know why some people don't have health insurance in the United States. So you gather some data, a very popular data set for many sociologists, economists, and public health researchers is the American Community Survey. It's this ongoing survey conducted by the US government. It's a really great data set, and it has a huge sample size. And you might gather this data, and you might say, well, in general, how likely is it that Americans are uninsured? How likely is it that people living in the United States do not have health insurance? Well, this is the data set. It's the American Community Survey data set. It's a sample of a sample. So we've restricted the size of the data set to a much smaller number just so it's manageable. But we can see that each row of this data set is a different respondent. And then we have several variables, including the respondent's sex, whether the respondent is married, their identified racial or ethnic identity. We have whether or not they are a US citizen. We have this variable on whether or not they have health insurance, and this variable for whether or not they are considered economically poor or not. And then we have a variable for whether they are a young adult or not. And these are all categorical variables, and for this kind of analysis, we might say, well, we want to look at this variable health insurance. So the first sort of analysis is if we just want to know how likely, based on this data set, that somebody is going to be uninsured, you can create a basic table of proportions. And so here we have a table of counts and a table of proportions. The table of counts shows that in total we have 343 people in our data set. 40 people do not have health insurance. 303 people do have health insurance. And if we just divide by the total sample size, 40 divided by 343 is 0.12. And then 303 divided by 343 is 0.88. And then 343 divided by 343 is 1. So that's the sort of total proportion. And you can see here that the proportion of Americans without health insurance is 0.12. So roughly 12% of Americans, based on this sample of data, do not have health insurance. Now this proportion we might want to treat as a probability. The idea of a probability is that it tells us how likely an event is to occur or to not occur. So just treating that proportion of 0.12 as a probability, we might say, based on this data set, the probability of being uninsured is 0.12. But we might want to ask, what does this really mean? What really is probability? Well, before we talk about what a probability measure really is, I think it's important to talk about why probability is so important for not just statistics, but just for conducting any kind of analysis on the world around us, just to kind of understand what is real or not in the world. The reason probability is so important is that it's vital to most questions that we're interested in exploring in various fields, from biology to medicine to sociology to history. So here's some examples. You might ask, well, if you have a diagnostic test, what's the probability it will give a wrong result? So we have screening tests for whether a patient has breast cancer. Now, these screening tests, these diagnostic tests, they're not entirely accurate. Sometimes they will give you a wrong result. Sometimes they'll say somebody has breast cancer, when in fact they do not. And we want to know, a good test, it's going to be accurate quite often, but we want to say, how likely is it to give a wrong result or a right result? We might say, in general, if you're a sociologist, you might say, well, I want to know how likely it is a person is going to commit a criminal act. And you actually see police departments now gathering data and trying to figure out what neighborhoods or what groups of people are more likely to commit a criminal act. This is expressed in a language of more or less likely. It's expressed in terms of how probable something is to occur. In this example that we're talking about right now, you might say, well, given you're economically poor, you're economically disadvantaged, how likely are you to have health insurance? How probable is it that you will have health insurance? So we can see that a lot of the kinds of questions we ask in various fields involve some language of how probable, how likely something is. Now, I should step back and say probability, it's actually really new. It's, I think one thing to keep in mind is that we've dealt with uncertainty for as a species for centuries and centuries. But the actual basics of probability, it's pretty recent. It's only really, it was developed in this sort of mid-17th century. And then it was really only formalized in the early 20th century. So when we talk about probability, this is all actually really sort of a new development in human history. The other point is that, and this is related to the idea it's a new invention, probability is often counterintuitive for most people. And I think this is where some people get tripped up, because probability starts out very easy, but it can be subtle in a way, and it can be deceptive in a way, because a lot of people think, well, it starts out easy, but actually it can be quite difficult, and people, very smart people, often mix up probabilities. They get analyses wrong because they're not thinking about probabilities in a logical or correct way. And I think part of that has to do with the fact that humans, we tend to use intuition, emotion, habit, or sort of rules of thumb, heuristics, and probabilities are really built on logical relationships. And so, I think one way to think about it is that you have to learn the rules of probability. Most people have to learn it. It doesn't come natural to them, but it's very useful because it can help you think in a more logical and clear way when you learn about probabilities. And then, of course, many intelligent people have been baffled by probability. So we might say, what is probability? Well, probability is simply a measure of uncertainty. It tells us how likely or how probable an event is to occur. Now, we can calculate the probability of just about any kind of event. When we talk about an event, it's just some observation of some experiment. It's some outcome that we observe in the world around us. So we have lots of different kinds of events. And these events we can assign probability values to. So I think when you first learn probability in high school or in elementary school, we talk about an event in terms of getting ahead when we flip a coin. So that process of obtaining a head on a coin when we flip it, that is an event. But we can think of lots of different kinds of events. So you might say, well, the idea of having heart disease after eating trans fats, that can be viewed as an event. We might say working more than 40 hours a week leading to depression. That idea of observing depression, that outcome, that can be viewed as an event. In our case right now, we're talking about health insurance. Whether you have health insurance or not, that can be viewed as an event. So we can think of events of many different types. A related concept has to do with this idea of randomness. Now, when we talk about randomness in statistics or data science, it means something slightly different than how you might have heard what randomness really is. To put it another way, when people hear the word random, they think of chaos. That's not actually what we mean when we talk about random in statistics or data science. We just mean that there's some uncertainty. It doesn't mean that it's helter-skelter. There's usually some kind of signal, there's some kind of structure to the event, but the idea is that we're just uncertain. You're uncertain whether or not the coin will be heads or tails. But you do know that if you flip a coin and it's a fair coin, half the time you'll get heads, half the time you'll get tails. So it's not chaos. It's just uncertain whether any particular flip of a coin will lead to heads or tails. So one way to think about random phenomenon, it's just we're uncertain about what's really going on. But we like to place some structure. We like to impose some structure on random phenomenon by specifying possible outcomes for each repetition or trial of the random phenomenon. And these possible outcomes, they must be exhaustive and mutually exclusive. So when we talk about exhaustive, the idea is that all possible results of the random phenomenon must be listed. And when we talk about exclusivity, right, the outcome of the random phenomenon, it cannot fall into two outcome categories at the same time. And so when we talk about exhaustive and exclusive outcomes, we can talk about a sample space. A sample space is, we denote it by capital S, and then we just list the possible outcomes. So if you have two possible outcomes, K equals two possible outcomes, you might say we're flipping a coin. One possible outcome is heads, another possible outcome is tails. So when we list those two possible outcomes, that's the sample space. It's the two possible outcomes. Now, sample space, in fact, can be infinite. But for now, we will just talk about a sample space in terms of these discrete possible outcomes. So here's an example of sample space of weight gain. Suppose we're looking at this random phenomenon of weight gain. It's random in the sense that there's some uncertainty about gaining weight. Now, when we talk about weight gain as a random phenomenon, we might want to impose some structure. We want to think about possible outcomes, and that way construct some kind of sample space. When we talk about a sample space of weight gain, we want the outcomes to be exhaustive and exclusive. So one possible sample space would be that you gain weight or you do not gain weight. So that is a correct sample space in the sense that you can either gain weight or do not gain weight. So they are mutually exclusive, but it's exhaustive. It covers all sorts of possibilities. If you don't gain weight, then the only other option is to gain weight. But a different way of imposing structure, of specifying the sample space, you could say, well, you might gain weight, you might lose weight, and you might have no change in weight. Again, these possible outcomes, they are mutually exclusive and collectively exhaustive. We're covering all sorts of possibilities here. A different version, again, these are all correct ways of imposing structure on this random phenomenon. You could also say, well, you might gain 10 pounds or more. You might gain more than 0, but less than 10 pounds. You might have no change in weight, or you might lose weight. Again, just a different way of specifying the possible outcomes when we're talking about the process of gaining weight. So there are many different ways of imposing structure. The key point here, though, is that when you specify the sample space, when you specify the possible outcomes, they must be mutually exclusive and collectively exhaustive. If they aren't, then it's not a valid sample space. So you could say, okay, the sample space is gaining weight or losing weight. Well, that is not a valid sample space because they're mutually exclusive. You either gain weight or you lose weight, but they're not collectively exhaustive because you could stay the same weight, right? Another sort of sample space you might come up with would be that you don't have any change in weight, you lose weight, you gain up to 50 pounds, or you gain more than 10 pounds. The problem is that even though these are exhaustive, it's covering the entire set of possible outcomes, they're not mutually exclusive. The idea is that if you gain weight and you don't gain weight, they're mutually exclusive and collectively exhaustive outcomes. So that's a valid sample space. So you have to be careful when you're specifying the possible outcomes. So once we're at this process, we've imposed structure on some random phenomenon. We've said, here are the possible outcomes, and these possible outcomes, they're exclusive and collectively exhaustive. At that point, you assign probability values to each of these events, these possible outcomes. Now, when we talk about some event, we use this language of probability. We say, if you have an event A where an event might be flipping heads, you'd say, well, the probability of that event is probability of A, or sometimes you'll see it as PA. That's just saying that's that value. That's the probability of that particular event A. Again, all we're saying is that that's just the chance that this particular event will occur. And a probability would range from 0 to 1. A probability of 0 has no chance of occurring, and a probability of 1 means that that event has an absolute chance of occurring. It's absolutely certain. So probabilities range between 0 and 1 inclusive. Now when we talk about probabilities, especially when we're talking about data sets, we can think about probability in terms of the observed frequency of an event in a set of data. This is a little bit different than the way you might have thought about probabilities in high school or elementary school when we're talking about games like flipping a coin or throwing a die. When we have a data set, it's often useful to look at the data and say, well, the observed frequency of an event, okay, this is really the basis of probabilities. So you can view each observational unit of interest as a trial. So each row of a data set, it's a different trial, it's a different repetition. And so when we talk about a data set, you can view the probability of an event in terms of the number of trials in which that event occurs divided by the total number of trials. To put it another way, you can think about the number of people in which they have that particular condition divided by the total number of people in your sample or population. So that'll be a little bit clearer when we go through the health insurance example. But the point now is that when we calculate this probability based on a data set, we get this value, which is a proportion between 0 and 1. And so 1, we have a certain event. So certain events, just to keep in mind, they're really quite rare. Okay? It's like the old saying, nothing is certain in life except death and taxes. So a certain event, probability of 1, you're not going to see that often. An even chance is 0.5, so that event is equally likely to occur and to not occur. And then when you have a probability of 0, it means that that event, it's impossible. It doesn't occur. So you can view a probability as ranging between, it's less often than not, so if it's below 0.5, it's less often than not. If it's above 0.5, it occurs more often than not. So you can see probability is quantifying how certain we are of some event occurring or happening or existing. Now when we talk about probability, we express in terms of 0 to 1 inclusive. A slightly different notation is in terms of odds. So odds, it's simply the ratio of the number of outcomes in which an event occurs versus the number of outcomes in which an event does not occur. So the probability of flipping a fair coin and having that coin land heads up, that's 1/2, that's 0.5. But when we talk about odds, the odds of a fair coin landing heads up, it's 1 to 1, because you might get 1 heads to 1 tails. So it's 1 to 1. It's a similar sort of approach as probability. It means the same thing. But sometimes you will hear people talk about odds. If you take more stats courses, odds are very important, especially in various fields like biology and medicine, where we might talk about odds ratios. But for now, just keep in mind, if you hear the word odds, it's just a slightly different way of quantifying how certain or uncertain we are of some event actually happening or occurring. Now, when we talk about the basic rules of probability, we can talk about 3 rules of probability. The first rule of probability is that that number, that value, must be between 0 and 1 inclusive. So we've already seen this. But just to formally put it into place, you cannot have a probability of an event above 1 or below 0. You can't have negative probabilities. And so if you get a probability of negative 0.5, you know something is wrong. The second rule of probability is simply that the probabilities of all the outcomes in some sample space, if you add up all those probabilities, it must equal 1. So we denote the sample space as S. So the probability of the sample space must equal 1. And I think that, that makes sense because that's a valid sample space. The outcomes must be collectively exhaustive and mutually exclusive. So when you add up all those probabilities in some sample space, that must equal 1. To give an example, if you flip a coin, you have a fair coin, you have a probability of 0.5 of getting heads and a probability of 0.5 of getting a tails. You add up those two probabilities for that sample space, and you get 1. 0.5 plus 0.5 equals 1. So if you have a sample space and you add up the probabilities for each of these possible outcomes, and that sum is less than 1, then you know you're missing an outcome. If that sum is greater than 1, then you know you're violating this principle of mutual exclusion, because in essence, you're saying two possible outcomes can happen at once. So one way of checking that your sample space is valid is to simply add up the probabilities for each possible outcome in your sample space, and that must equal 1. Now, if you're working with a data set, there might be some rounding error, so I wouldn't worry too much about it, but the basic idea is that you want that sample space to equal 1. The third rule of probability is known as the complement rule. The complement rule simply says that if you know the probability of some event, then 1 minus the probability of that event will tell you the probability of that event not occurring. It'll give you the complement of that probability. Now, when we talk about the probability of some event not occurring, we denote that with usually a line over that event or a little hash mark. It means the same thing. One thing to keep in mind is that that line over that event, it is not the mean of A, it is not the mean of some event, it simply is a notation for telling us that that is the probability of that event not occurring, right? So one thing to keep in mind when we talk about basic probabilities is that it's often useful to visualize them in terms of Venn diagrams. Now, when we talk about Venn diagrams, if you understand Venn diagrams, then you will understand this joke. But we can think of the world as consisting of those who can read Venn diagrams and those who can't read Venn diagrams. Now you might say, well, what is this? What is a Venn diagram? Well, a Venn diagram is simply a way of partitioning out the sample space. So here are the three basic rules expressed in terms of a Venn diagram. That circle gives us the probability of some event A. And then that probability of that event A, that probability must lie between 0 and 1 inclusive. And then that region outside that circle, that will give us the complement. That's the probability of not A. And then we say, just as a reminder, the probability of A and the probability of not A, that's the probability of 1. So the probability of the sample space equals 1. So let's return to our example of health insurance. Again, we're imagining we're some kind of public health researcher, and we want to know how likely is it that an American is uninsured. And so we collect this data set, and then we create this table of proportions. And we find, well, 0.12, that's the proportion of people who do not have health insurance. Now, we can view this as a probability. The two possible outcomes of our sample space are that you don't have health insurance or you do have health insurance. So we can view the sample space as no and yes. And these outcomes, they are collectively exhaustive, so you cover all sorts of options, and they're mutually exclusive. Okay. For the purposes of this example, we're not saying that you can't have health insurance and not have health insurance at the same time. You either do or you don't. So we can view this as a set of possible outcomes, and with probabilities. The probabilities attached to each one of these possible outcomes. So the sample space is given by no and yes, and then the probabilities are derived from that table of proportions. So we might say, what is the probability of event I, where I is having health insurance? Well, the probability of event I is 0.88. So it's more likely than not that you have health insurance based on this set of data. Now let's talk about the complement, which is a probability of not I. The probability of not having health insurance is 1 minus 0.88, which is 0.12. Now both of these we can conceive of as probabilities. They lie between 0 and 1 inclusive. And you can, in essence, say, well, okay, the probability of not having health insurance, it's less often than not. So it's, it's not likely that that event is to occur. But we can also say that if, the probability of having health insurance is relatively high, 0.88. So based on this sample of data, we can make some conclusions about how likely it is that Americans are to have health insurance. So we might say, well, the probability of having health insurance is 0.88, and the probability of not having health insurance is 0.12. And with that, we've really started our discussion about taking a set of data and expressing this data in terms of probabilities, how likely something is to occur or not.